Greetings, guys. So I will be talking about a quick architecture overview. As Jeremy says, we will be covering the foundations, a higher level in terms of architecture. Okay, I will. My plan is go through those contents. So from the general overview, what I'm calling here the backend flow. We will see what backend means here, but it's the process that manages that connection and what it does. The auxiliary process, which means here everything else that is not the backend process that's handling that connection. Then we will talk a bit about the disk layout and how things are organized internally on Postgres. And then, because we are talking about the disk layout, we will talk about the pages and tuples. And Postgres usually we call pages when it's in memory, but it could be also the data blocks inside the data file, inside the table data file. Then we will talk about the multiversion concurrence control, the MVCC, that we can argue that it's one of the core components inside the Postgres database, because how it handles not only the concurrency, as the name said, but how it handles the locking system, the concurrence through multiple connections trying to do multiple things at the same time. Let's say if I am managing a bank, I need to withdraw money from my account and deposit money on Jeremy's account. And I want to that operation occur in the most atomic way. But if the money goes out from my account, I must be sure that it goes in Jeremy's account. Otherwise, it should not be out of my account. And then MVCC is there to ensure that in the easiest way possible, and by easiest I mean from the resource utilization viewpoint and how the algorithm handles that, and the possible ways to control that. But that we will see that bring few issues in the long run that create old versions of tuples that will require vacuum. And that's one component that's very specific on Postgres. And then we will glue everything together, talking about the shared memory and the write-ahead log mechanism, and then checkpointer and background writer. And that will be then very high level covering those things. So I will try to not take more than 60 minutes talking about that. But for sure, we could spend one day talking of one of each component here. So the idea is giving a general idea. I will share this deck after this presentation, which has few links as well for each one of those topics, okay? So just a brief word here. So what is Postgres and why it's Postgres? It's something that's not new. Probably there are few people that will imagine that Postgres is some hype thing that is just happening from the last 5 years, but it's a very stable and solid project that was created in Berkeley in 1985. And the name came from an old database named Ingress. So the Postgres is post-Ingress, that's the name. There's a vibrant community online and presential community that you can seek people all around the world to discuss ideas, develop together, and share your ideas. It's a free software, but by free, usually people have this concept that free means I don't need to pay anything. and you don't need to pay for the license, but it means that you still need to pay for support, you still need to pay your DBA, you still need to pay for taking care of your database. So we could translate that for a low cost of ownership due to the Postgres licensing. So yeah, there's professional commercial support, as you will see in any other engines like SQL Server, Oracle, Sybase. Yeah, it's another database. And another thing that I could mention here that I think it's worth to mention in an open slide is that Postgres has a very clear versioning policy and a development cycle, release nodes. So it's very predictable how new features are released, how bugs are patched, why you should keep on the latest minor version, things like that we can discuss it later on. Okay, so to start talking about the architecture, we need to understand how the client, the application, connects with the database. And there's a very simple diagram here that we will say that Postgres, the client, the application, will use the libpq, that's the client library, and the libpq will open a connection and try to authenticate with the postmaster. This authentication will fork another process inside Linux, and that other process will be responsible for that connection. Here we are talking about libpq, but it could be JDBC driver, for example. Then that backend process, of course, if you have 50 connections, those 50 connections must know what each one is doing. They need to understand that if I'm open a table and other session is open the same table, what that session is doing, I'm allowed to lock that table or not. And that integration and that communication between those processes, it's done through the shared memory that's pre-allocated when the postmaster is launched. Then, of course, you have kernel stack that will handle disk buffers and the storage itself. Okay. One detail that's important to mention here is that the Postgres protocol is from 80s, so it's very detailed in terms of how it's implemented, and at that time it was assumed that TCP was not a standard yet, so you have somehow re-implementation of a few things that you have given on TCP/IP that's re-implemented on libpq. Okay. So you will see that each connection now it's handled by a different process ID, a different backend through those fork processes. Okay. And each backend is also responsible for its own authentication. So you kind of fork first to have that process authenticate for you, and if that authentication is wrong, your password's wrong, your user's wrong, then the process will terminate itself. So yeah, libpq, it's a client-server protocol, and you will use the socket interface nowadays to communicate through TCP/IP. Then we will talk also about the auxiliary processes and how the auxiliary process and those backend processes are tied together with the shared memory. So the disk layout and how files are distributed, we will see that there's the database cluster, and the cluster word specifically is can create some sort of confusion for the user that's seeing it for the first time on Postgres community, because cluster here does not mean a set of instances or different machines as you wish. It means a set of databases inside the same instance. And that's the terminology used in the Postgres documentation, that sometimes if you are reading it for the first time and see the word cluster, for example, pgctl restart the cluster. But you say, but I don't want to restart the cluster, I want to restart just this instance. Yeah, your instance is the cluster because it handles multiple databases inside the same instance. And it's a concept that Postgres has from pretty much from the beginning, that you can have multiple databases inside the same instance. You don't need to have multiple instances to have multiple databases, okay? And this is something very specific on Postgres. So you have like inside the cluster, but we can replace that word cluster to make it easier to understand that cluster here means instance. So we have the database instance, which has multiple databases, DB1, DB2, DBN. Those databases, they are isolated from each other, so you cannot join one table from database 1 with database 2 easily. You can do that, but you will need to do a link, a DB link between those two databases as you are doing a DB link with another instance, okay? Because they are really isolated from each other. But then you have DBN here that you can have multiple schemas. And by schemas here, we can understand like logical containers, okay? So I can have my public schema, that's the default schema, but I can have schema HR, schema accounting, schema marketing, and each one of those schemas handling objects for their own business. And then those schemas, I can join tables from different schemas inside the same database. That's given, I can have foreign keys between them. So, and another thing that people will create some confusion when coming from Oracle, that sometimes schema will mean user and user will mean schema. But here they are not related with the user that connects with the database. So schema is just a logical container. It's just, we can do analogy like it's a directory when I put my files, my objects. But this is just an analogy, okay? Schema is not a directory. It's just a container, a logical container, which I can use to divide my objects with a logical meaning. Like I say, accounting, marketing, HR, and put objects in a different schema to have it organized, okay? Or even I could have, depending on my data model, I could have different schemas for different companies or different business units, and then I can merge them together. It really depends. It's very flexible. Internally, on the host, each database is a directory. There's a specific directory with an ID, which will contain all data files for each table or each index or each sequence that's inside that host, which will be used by the postmaster, okay, in the backends. And then we need to start talking about the backends, okay? How the backend works. Remember that the backend here is the process inside the Unix that handles your connection, okay? So he's responsible for your session. So for start, I can already say that because one process is designed to handle your connection, if you have 1,000 connections, you will have 1,000 processes to deal with each one of your connection, okay? So there's a very good slide from Bruce Mongen here that tells how the back end will behave when the statement is coming from the application, okay? So there's another cut here from what we see in the previous slide when the libpq is responsible to connect the Postgres with the application, which we can see that it's the main here. Then this green square is the backend behaving and the workflow inside that green square is the sub modules that is inside that backend. So we will talk about the parsing phase. We also have the traffic cop that will be used to divide which is a complex query and then from what is a simple command. And by complex query here, we are talking about selects, inserts, updates, and deletes. Not really complex in terms of how big your query is, how if there's joins or not. Complex is everything that's not a command. And by command here will be a copy, a create table, an alter table. Those things will be the command utility. Then we have the rewrite phase that nowadays will be used more to decode views into queries. Then we will have the generate paths and the generate plans, taking in consideration the statistics that is constantly collected by the auto vacuum workers, and of course if you run analyze. And then you have the execution phase, the execution plan. This process can retroalimentate itself if you have subqueries and if you have store procedures or views. And then finally, when the executor goes on, it gives the result back to your client. So what I try to do in my next few slides here is to dive deep a bit into which one of those phases, okay? And as I mentioned before, each one of those slides has a few references and links to sometimes docs or Postgres source code from the implementation of that part inside the backend. So that might help us to dive deep later as well. So one thing that the libpq thinking here in the client side have in mind is that it's a custom protocol, so it must take pretty much the heavy lift of network communication. Even if it's implementing on top of TCP/IP, you must control network timeouts, you must control if it's a security connection, it must use a library for SSL connection, but it must call those functions itself inside the LibPQ protocol. So there's a lot of settings that you can do, both on client side as well on the server side, to manage how this protocol will behave. It has few other features as well. For example, asynchronous notification, listing notify command on Postgres that can be used to do queuing. So this is a very good feature from the LibPQ itself. The native SSL support based on SSL libraries that I mentioned is that thing that I was saying, that we have a library that implements the SSL connection, but how that implementation calls those functions is done by the LibPQ itself. The LibPQ also implements the book import-export through the copy command, the copy statement. That's very useful to do large operations when you are dealing with a large table. 1 million rows I want to get from a CSV and import in a table. I will not do this doing 1 million inserts, because it will have the overhead in terms of parsing that statement, of doing a lot of extra work. So if I already know beforehand that I need to insert 1 million rows or registers from a CSV file, I must use the copy command to make it faster, okay? So then, following the arrow here, we see that the LibPQ connects with the backend, okay? And what the backend or the backends, the multiple processes that we have for each connection that we have, will do now. Those multiple processes, simplifying that flow, will do the parser, the optimizer, and the executor phase, okay? So the parser, the first thing the parser will do, it's a lexical analysis. It's make sure that the syntax that you are using, it's a valid syntax, it's a valid grammar. If you are not misspelling some command, if that command it's making sense from the SQL grammar that's implemented inside Postgres, okay? And that is done using few things here. There's the file for the lexical analysis and the grammar itself, that it uses Bison and Flex. That's an open source tools as well that implements those parsing languages, okay? The result in this phase will be a parse tree. And we can think in terms of decoding the language, the SQL language, in structures that will say, if I'm doing a select, which C functions inside the source code must be called to do the select. Sometimes you take a simple select star from table A. By a given, some database magical thing internally will do that for us, but we need to remember there's some source code doing that for us. And to do those things, we need to decode the simple select in terms of C operations, C functions inside the database code to do that. And that it's done in this phase here, okay? Of course, if instead of select, I misspell the select and I add an extra E on the end, that command is invalid. The SQL grammar does not implement a select E with the E in the end, so it gives an error. That command is invalid. That's done in this phase here, okay? It will generate a parse tree tree is a data structure in the memory that will represent that command that you are trying to execute. But by that time, you are not validating objects yet, so you don't really know if the table exists or not, if the column exists or not. What you have now, it's the parse analysis, is to add those things. Okay? It's the function exists. If you're trying to call a function to decode timestamps to string, it's done in this phase. And then you have the rewrite phase, which I mentioned before. It's most used nowadays to replace views into normal queries, but you can also manipulate the rewrite directly. You, I mean, the developer, the DBA, and do some trick stuff, which is not recommended nowadays, but still can do that. For example, if I try to insert something in a table, instead inserting that table, I insert in other table. That's possible, and sometimes it's useful to know that it's possible to do that. So that's done in the rewrite phase. That I think is something very specific on Postgres. It's not triggers. It's something, I could say, lower level than triggers. And it's something interesting. Okay, so now we have the parse tree, and we need to know what to do with the parse tree. We already know that the command exists. The command represents those C functions, and those C functions will try to access object table A with columns C1 and C2, for example. So now we need to understand how I will do that. And by how, I mean, should I use an index to access it? I'm talking about the entire table or just one row in that table. If I should use the index, which index I should use? Those things and those operations are done here by the optimizer, which will be decoding the parse tree to get an execution plan. Okay, if I'm doing a join, what's the join method that I will do? A hash join, a nested loop. If I'm using an aggregation, how that will be taken in place. And that phase, the optimizer phase, will get the parse tree. That it's the, we could consider it the table plus statistics. Sorry, the table statistics plus the cost parameters, and get the execution plan tree. Okay, and that part is important for a DBA. What is the cost parameters here? The cost parameters, we could imagine like they are the factors that represent your host, your environment. And by factors, I'm talking about absolute factors exactly. What's the difference between a random access and a sequential access when I'm trying to get a row in your database? It's a way how you can control the optimizer itself by manipulating those factors. Okay, so it's a kind of external knobs that you have to manipulate how the optimizer will behave. So it's important for the DBA understand the optimizer behavior itself and how those knobs interfere with that behavior based on the query that he's trying to do. And there are multiple cost parameters for multiple different actions that the optimizer will generate. Those actions is the execution plan tree. Once the execution plan tree is done, is pretty much it, is that how Postgres will access your data. So you have already the the final plan to execute that data, okay? You know that there's the command explain that allows you to observe that plain tree. It's pretty much the output from the operation. So the explain will generate, and you observe those costs. You observe how much time it should take. And if you run the explain analyze, it gets the real data after the real execution. So when you run explain analyze in a query, it pretty much get everything, the time on each one of those phases. How much time you take by join the table, how much time you take in the where clause, how much time you take aggregating that value that you receive from that join. Everything you get, and you get those metrics from there. Using the explain analyze will give you the best idea of how much time your query will take. So developers constantly talk about test-driven development, for example. And it's interesting that sometimes you forget to add an explain analyze for queries that you are doing in the application to get those metrics. And it's pretty rich in terms of metrics. So it's some good practice as well. Getting the explain analyze of the most common queries that runs and interpret those data and see if that it's skewed in terms of what I would expect that behaves or not. Okay, so then the executor. The executor, once you have the execution tree, we will get a copy of the plan tree, which it means the state tree that will control which step is being executed, okay? And of course, the executor needs to know about the memory management, the transactions, access methods, how I access that row internally in the page. And then I go to the access itself. That's how the access is implemented for different types of objects that I can access. For example, if it's an index, I have different types of indexes. That's something very good on Postgres. I have even a possibility of extend how an index works using those special index types here. Balanced tree, rash, gene, gist, special access methods for indexes. And then the heap itself. Heap, when we see heap in the source code, is a table access, the raw table access, okay? And that will be the end of the execution phase. And then you get the data from the disk or from the memory, depends where your data already are, and give that data back to your application. So we see there's a lot of things implemented internally on the simple backend that's handling your connection. It's not just handling your connection, it's doing all database stuff that you want to do. Okay, so now we need to talk a bit about the auxiliary processes. And I would just try to cover it as fast as possible because there's a lot of auxiliary processes. Auxiliary process here, it's everything that it's not just the backend that's handling your connection, okay? We have auto vacuum, stats collector that collects activities from your database, information about how much that table was accessed, how much, how much the number of, how many is the number of dead rows, the dead tuples inside that object, okay? And then we see the wall writer, that's responsible for controlling the execution of the redo mechanism on Postgres. So we have the backend process here when trying to access the shared memory, getting the wall buffers, writing using the wall writer mechanism to the wall files, which will after be used by the archiver to send this to an archive storage. Okay, so now going a bit deeper in terms of pages and the memory itself, and how is the data structure of those processes, what those processes are trying to do, what's the fine granularity in terms of data internally in the Postgres. So we already know that we see the backend process here, and each process has its own memory structures for temp buffers, workman, and maintenance workman. Pretty much we can highlight the workman here for hash joins or any sort of internal operations that the backend is doing. For example, joins, as I mentioned, aggregations, orders. If your query relies a lot of memory for those operations, it's a parameter that you can increase. And then you have a shared memory, a global pool here that all those processes will talk with. So one process knows what each other is doing. And then that memory, the shared memory, will be synced with the data files itself. If we go a bit deeper in terms of the data structure, we see that there's the data directory, and there's a directory for each database and one file for each object. It could be an index, it could be a table. That file is divided in 8K pages, okay? And then if we zoom into those 8K pages, we have the page reader, and we have item pointers, which will point to tuples in the end of that data structure. So we have the header and the item pointers from the top point to the end of the data structure, and they will meet in the middle. Once they meet in the middle, another page will be created. Of course, roughly speaking here, there's a lot of things that we need to understand when we go deep how those things are manipulated. Okay, we can control the empty space here that is tolerated or not. How soon you need to create a new page. Okay, so just a bit of zooming in here. If we take that previous slide where we have multiple 8K pages and the item pointers going to tuples, those tuples here, if we zoom in, and then we will see that the tuple itself has a header. So it's not the header for the page, okay? It's not the header for the page, but it's the header for the tuple itself, which has few interesting columns here that we can discuss later. And then the values itself, okay? Values for integers, for text, and then the next tuple, okay? But the next tuple is before. If we're looking from right to bottom, the next tuple will be after. And of course, it's always possible to learn more, and there are a few interesting ways to learn more. That it's using the page inspect extension, the file dump. It's a third-party tool that allows you to see the file itself in the storage folder inside the Postgres source code. Okay, then now we talk about pages and we talk about those data structures. We need to understand what is multi-version concurrence control. Understand it's very it's kind of presumption of mine saying understand, because I don't say that I myself understand fully the MVCC. It's a very complex algorithm, and how it's implemented, it's very, very complex. There are a few videos that I can share with you that I'm using to learn about it myself. But we can talk about the purpose and some strategies that the MVCC does use to do its job, okay? So the purpose is maintain data consistency internally. So if I'm trying to change a row, I must ensure that the change will be consistently applied if I commit that change to other objects, to other sessions, that is observing that change. I also must ensure that readers will not be blocking writers, and writers will not be blocking readers, at least for DML. If I'm inserting, if I'm updating, or if I'm deleting, selects will not be blocked by those operations. Then, of course, depending on the operation that I'm doing, for example, changing the table itself and adding an extra row for a few period of time, for a short period of time, that will block the object, and it's a write operation. So yeah, readers not blocking writers and writers not blocking readers in the day-by-day operations. Of course, there are operations that might block your database, and we need to have that in mind when we are talking and with DBAs, because sometimes we can observe people say, okay, I'm creating an index here, or my application is down, because creating an index without the concurrently parameter will block your table for everything else. Okay, so that's something that you should know. And yeah, another things that MVCC does as well is provide transaction isolation in concurrent transactions, prevents transaction from viewing consistent data. It's that example that we are talking before. If I want to do a transaction, a cash transaction, if I want to transfer money from one entity to another, I want to do in the most atomic way. So the MVCC is controlling that, okay? And to do that, it will need to use a few locking and locking modes internally. We will see as well how it will lock the shared buffer to not allow other process get that data, what we'll call a latch or a lightweight lock. Of course, I need to persist the state of each transaction, if that transaction was already committed or not, and if that transaction was aborted, for example. So we have a few mechanisms to do that for the transaction itself, but also remember when I was talking about the pages and the header, we have a few concepts in how this is implemented on Postgres. For example, the xmin internal column tells about the ID that creates that row, and the xmax tells about the ID that deletes that row. And which ID is it? The ID of the transaction. And the MVCC implements that mechanism to understand that row was deleted. How the Postgres, how the backend knows that the row was deleted, because there's an Xmax on that tuple. Okay, so I like to use the tuple in terms of the physical row, and row is the logical row that you see, your application see. But your application might not see a physical row that was already deleted before. And that's interesting because that may raise the question. So you are telling me that if I delete a row, the row is not really deleted? And yes, that's true. If I delete a row, you will keep another version of the row, the previous version of the row, and you will need a mechanism to clean that row that we call vacuum, okay? So vacuum will keep the pages clean, removing those rows, those tuples, better saying. So the premise here is when a row is deleted, behind the scenes, there's a tuple, okay? And the tuple is just marked as dead. I don't need that tuple anymore. The same thing will happen on an update, okay? Just an advice for architects and developers. If you update constantly, it means that you need vacuum constantly as well, because update creates a new version of that tuple. So the vacuum will clean your page. There's a cost involved on that requires I/O, requires CPU as well, but it's not. It's a cost that it's worth that cost, because how the MVCC works is that makes very fast to roll back an operation and even to insert a new row. So the trade-off is very good. There are 4 types of vacuum operation, okay? There's the normal vacuum that reclaim dead tuples from pages by removing those pointers. There's the full vacuum that also reclaim dead tuples from pages, but in fact, it's not, the wording here is not really good, because what the vacuum full does, it does recreate the entire table and indexes from scratch. So it's pretty much a deep copy of that object physically into another object, and then switch the catalog. And that operation will do an exclusive lock from the beginning to the end. There are a few alternatives to vacuum full, okay? There's the vacuum freeze. That's very important about how the MVCC itself works. And the vacuum freeze, it's used to prevent the transaction ID wraparound phenomenon here that will be very important when we are doing few labs. And then the shared memory here will glue everything together, okay? The shared memory, a few cuts of the shared memory itself. The shared memory is, of course, the representation of everything together. The write-ahead log, it's the redo mechanism that will facilitate how changes are made in those data files, okay, and ensure the durability of those transactions. So if you commit, you be rest assured that the commit is already in the disk, but also it will give you as fast as possible the return of that commit. The commit will not take a while to be flush in the disk. Okay, so having that previous slide in mind in those phases, the executor itself needs to do a few things to ensure the commit is done. for example, in case an update that you are committing, it must update the shared memory. And then it needs to ensure that that change is physically on the WAL files, or redo logs if you are used to Oracle terminology. Okay, the implementation of each one of those phases here are linked. You have the xlog insert. That's how the transaction is always appending the WAL file. Okay, for each change that you do, it could be a maintenance change like a vacuum. It could be when you are creating an index or changing a table. You are always appending the WAL file, the transaction journaling mechanism. Okay, a journaling, if you compare with a journaling file system, it's a fair comparison. The WAL file that keeps the transaction with a journaling mechanism in the file system. So then we have the check pointer and background writer that will sync the dirt pages in the shared memory with the data files itself. So we have here an xlog insert, appending the WAL file after the shared memory is updated as well. In parallel, you will see the check pointer applying a record, a register in the WAL file, say, hey, I synced all files here in my data files. I synced all dirty pages on my data files. So if a crash occurs, it's safe recovery from there. And it will mark the WAL file from there. And the background writer will be constantly flushing the shared memory to the data files. The background writer was introduced not exactly at the same time the check pointer was introduced. So it was introduced to make the check pointer life easier and speed up the checkpoint operations. So in summary here, try to cover multiple aspects from the architecture. Each one of those, as I mentioned, there's very specific points that I think Jeremy would like to cover and dive deep with you guys and see which more we can learn from each one of those. Good.